Okay, so I'm just going to do a very quick recap of what we learned in these last days. So you have a general dynamical system, x2, x1, x2, or this could also be higher dimensional. It's generally time dependent. You compute trajectories that start at x0, arrived at f of x0 after a certain time interval, t0, t. Then we learned that the Cauchy-Green encodes all the possible Lagrangian deformation of any fiber, zeta 0. And yesterday we also learned that if you Taylor expand Cauchy-Green along trajectories and you evaluated the initial time, all this stretching or stretching rate information are basically encoded in the rate of strain tensor. This is how we defined the instantaneous attractors, and these two tensors are basically have the right properties because they are frame invariant or objective. So that means basically that they really don't care what kind of reference system you pick to describe the motion or deformation. And then, so yesterday or 2 days ago, we had some, preliminary, classification of coherent structures. They could be, hyperbolic, attracting and repelling, parabolic jets, and elliptic vortex type. They could be short time, finite time, or asymptotic. Okay, and again, as I said, there could be many other sorts of coherent structures likely that have not been developed yet. So you can define the new notion of coherence and define other types of structures. So what I want to do today, I want to try to explain a little bit the elliptic coherent structures, and I'm going to do it using the Eulerian formalism. Okay, but then eventually we are going to use the Lagrangian one, but the Eulerian one is a little bit easier perhaps to interpret, but they are exactly the same. So remember what we were doing yesterday, or the business in general, is this one. So you are in a particular region of your phase space, actually in your phase space. This is x1, x2, but again could be also higher dimensional. And then you want to look for some curves. Yesterday we looked for curves, the gammas that were the most attracting, and today we're going to look for curves that stay together. They are like, they play the role of vortex boundaries. So these new curves will be closed, right? Because that's how a vortex boundary is going to be. The properties of a closed, a vortex is basically surrounded by a closed curve. So then the property, the philosophy is always the same. You have to parameterize this curve. You don't know where it is. The business of this is just looking, finding where it is, right? So you parameterize this curve as x of s. X has two components into dx1 and x2. Then the x prime is the tangent direction, and n is just 90-degree rotation matrix R times x prime, okay? And this is just to have a coordinate base that moves with any point on this curve that I have to basically eventually locate. And now you start defining the interesting quantities that will allow you to define the type of coherent structures that you want, right? Yeah. So this is basically the material stretching rate. It's actually very similar to what we've seen yesterday. Yesterday, what we did, we said, okay, I want to understand what happens to a normal direction at any points on this curve, and I wanted to understand if this normal direction will extend. It's going to be a stretching rate or a shrinking rate to understand attraction and repulsion. Very similar. So basically what we did yesterday, we said, okay, this is the rate of strain tensor. It knows everything about stretching rate at any point and time. And then yesterday we put an R here, so Rx prime here, and that was basically understanding the stretching rate of the normal. Okay, if you want to understand how to define a vortex, instead of looking at the normal, you look at the tangent direction. So you want to understand any point in this curve. Eventually we are going to impose that is closed, but at any point in this curve, how much will I stretch? Well, what's going to be the stretching rate at any point? And that's precisely this, right? You see it. So basically s times x prime is going to tell you project s on x prime, and then project this value back. Okay, so there is going to be basically a quantity that tells you the material stretching rate at any point, at any particular time. Is this clear? Okay. Okay, so then you do the same and you compute the average material stretching rate on a curve, which is Q. I mean, in this case, you're calling it Q dot because this Q dot is really the stretching rate. So this dot is just to account for the fact that this is a stretching rate. It's not really stretching. And so this is one particular metric of deformation. Then there is also another one. We are not going to use it here, but for you to understand, if you want to understand now if across this line there is going to be a lot of shear, okay, then what you have to do, you just have to do a little bit of calculation, but it's nothing else than projecting how an initial normal will get sheared by this flow, and if you compute the projection of this normal into the tangent, you're going to get a metric that accounts for the shear rate, okay, which is basically all kinematic, okay. We're not going to use this quantity, but again, you define the material shear rate. You're going to define the average, similar average, functional on this curve gamma, and with these two functional, you can actually define all these structures. The hyperbolic, the parabolic, and elliptic. Okay, so you do the maximization as we did yesterday, and you can identify these structures. Okay, so I didn't put all the references here. George wrote a very nice review article. The parabolic work was actually done by Mohamed Farazman, which is a good friend and a professor at University of North Carolina in Chapel Hill, and that's when they developed the notion of parabolic Lagrangian coherent structures. George did previous work on elliptic Lagrangian coherent structures. You can just look at all the references in, or the history of this in this review article, and then instead, for all the instantaneous version, you can look at the paper that I did with George. So what I want to do now is say, okay, how do we actually define elliptic coherent structures, elliptic Lagrangian coherent structures? So what we want to do, we want to say that this functional, which is going to tell you the material stretching rate of a curve, is going to be minimized. Okay, because think, what's the philosophy here? Think about it. So if you have a vortex that is very coherent, you want that the vortex boundary is not going to stretch. When you basically think about, filamentation that I showed the other day, if you have an incoherent vortex, the boundary of this vortex will start stretching exponentially. Okay, that's what you see. I mean, for instance, you can have a very, diagnostic footprint of this when you see, the contours of the vorticity that gets crazy, stretched, and then the vortex basically dies out. This is a similar philosophy, but it's based on a metric that quantifies material deformation. Okay, so is this a little bit clear? I know all the details are not important, but what I want you to remember, parameterize your curve, use the tensor that has the right properties, frame invariant, objectivity, etc., and then you define your local quantity, the average one, and then try to minimize. Try to look for the gamma that will minimize that functional. That's a classical calculus of variation problem. Okay, let's try to do it now. So this is what we want to identify. So Q dot is really the stretching rate of any point on this curve, okay? And this is the average quantity, and then I want to take the first variation because I want to look for gamma that are extremizers of this functional. So there are going to be some gamma, some curves, in this case, such that if I perturb gamma a little bit, the functional Q dot is not going to change at leading order. Okay, so this is basically the classical problem of calculus of variation. When you basically take the first variation, you're going to get a boundary term that depends on boundary points or perturbation at the boundary points, and an integral term. Okay, now the interesting thing is that for closed curves, this boundary term is always 0. Because the initial point of the curve is equal to the final point of the curve, because the curve closes up. So this always goes to 0. And this is a big miss, because usually this boundary point will help us to understand at least where this structure may be. That will give you an additional condition of where this structure may be. But basically, when you have closed curves, we are losing this information. Okay, so you're just going to have the integral term from the variational problem. You compute the Euler-Lagrange equation, and you're left with this differential equation. Okay, now again, Q dot is just a function which is just depends on where you are, x, so points that you don't know where they are, and the possible direction on this curve, x prime. So this would be a particular x of s for a particular S star, and this is the local tangent to that particular point, okay? So this is Q prime, so these functions will depend on x, x prime, and t, because of course the rate of strain tensor usually depends on time. And then when you do the calculus variation problem, this Euler Lagrange, you're gonna get the first derivative with respect to x prime, but then you're gonna be hit by another DDS, which is the parameters for the parameterization, x of s. And therefore, this is going to be a second order derivative in x. So you're going to get something like, when you calculate this quantity, you're going to get a differential equation for x double prime. Okay? So what does that mean? When I have a differential equation, so x prime, again, this is basically, x of s is my curve. So when you know x of s, you know the curve. Okay, now I'm going to have a differential equation which is x double prime of s plus some alpha of x prime of s plus some x of s, beta x of s, plus some constant, if you will, and this is equal to 0, right? That's basically something of this form that you can get from this equation. So now, to integrate this quantity, remember x of s in this case is in 2D. So that means basically now to integrate this equation, you need 4 initial conditions. You need basically an x of 0, an x prime of 0. Okay, these again, they are vectors. This is basically a 4D initial condition. And the problem is this one now. So imagine you have this differential equation to solve, it's ready to go, but how do you know where to start? Right? And remember, for instance, if you are in a let's say in the ocean, only the two-dimensional subspace of this, only this part, which tells you where is the initial condition that I have to start looking at, could be, huge. So where do you start? It's going to be a very impractical problem, right? So this is saying, this is where x prime, x1 prime, x2 prime, x1, x2 is the phase space of this differential equation. Now I have to pick where to start. Let's forget about the velocities. That's also even higher dimensional space, because for any point you can start in many different, directions. But where would you start in an ocean or in a domain? So that was basically a problem, which actually goes back to what I was discussing with Anupan at breakfast. And Anupan was saying, if I have a two-dimensional dynamical system, how do I know where are the limit cycles? I said, good luck, because there is not really a super trivial solution. There are some conditions that are necessary. For instance, Poincare-Bendixson theorem tells you that in a regular vector field, the fixed points of the vector field inside the limit cycle should obey some laws, but that's necessary and not sufficient. Okay, and this is now not a regular vector field, but is a direction field, because this direction x prime is the same as x prime plus pi. Because if I percur in one direction, it will be the same as the other direction. So basically, these are basically limit cycles now of direction fields. Okay, so how do we fix this problem? So this is basically a four-dimensional problem. I have this beautiful equation. How do I solve it? So you can basically rewrite this problem as the null geodesic of a Lorentzian metric. This is a little bit of I think, a fancy notation that we used, but basically it's going to become clear in a second why we did this and how we overcome this problem. Okay, so basically, we say, okay, we can actually reframe this problem as a null geodesic problem, and now we're just going to focus on the elliptic structures, and I'm going to explain this in a second. So here. Okay, so basically, we want to look for this closed null geodesic of this Lorentzian metric. So what they do, basically, so again, we are looking at these curves. That's exactly what I basically sketched there. So we're looking for curves, x of s, parameter of the, the tangent. So the tangent vector is going to be x prime of s. I can just parameterize into this with an angle. Okay, and now, if I want null geodesic of this metric, what I did, I replaced x prime with the e of phi, just a unit vector in the direction of phi, the local tangent to this curve. I mean, I can get rid of the norm of x prime, because it doesn't really matter. I can percurve this curve faster or slower, but what I'm interested in is really the geometrical set of points of this thing. So I reduced the dimensionality by 1, just now looking at the angle. So my null geodesic is now satisfying this condition. Basically, you have a matrix, nothing else in a matrix. E phi, this is just a direction that depends on angle. And if you are on this curve, you can show mathematically that this equation must always be satisfied. Okay, so basically, you know A, this is just the rate of strain tensor everywhere in your domain, space and time. Mu is a parameter that tells you precisely how much stretching rate are you allowing. So if mu is equal to 0, it's completely non-stretching. If mu is 0.1, 0.2, it's slightly stretching. So those are slightly breathing, vortices, if you will. So I can plug in this value of mu. I know this matrix, and I have just this equation to solve. And basically, this equation to solve is going to depend on phi, the particular angle, so which I don't know. Okay, so this equation is always satisfied, and then you can write an alternative differential equation instead of solving basically this four-dimensional differential equation from Euler-Lagrange. You can have an alternative one which is simpler. It's going to tell you, look, the velocity should just be cos phi sine phi, and this phi dot is going to be some function of A. You can this is just the derivative of A, normal rotation matrix R times A. The details are not important, but the important thing is that you solve this differential equation and you're going to get this closed curve.
And this dx is capital dx?
The derivative of this matrix is depend on x with respect to x. So this is going to involve the derivative of s with respect to space. You're going to have a 3 tensor to play, but then you always contract it with the direction of phi. Okay, so now we transformed basically this 4-dimensional problem in a 3-dimensional problem, but with a lot of interesting property, because now this is going to be my slice of the domain. Let's say this black curve, so this is x1 and x2, and in the other direction I just have phi. Okay, that's basically, now I'm just, you can parameterize this curve with, where it is, but also you have to tell me what are the local tangent to these points. So there is a phi, okay? But phi lives in S1, it's a periodic domain. So basically this phi is always gonna go from 0 to 2 pi, because I'm looking for closed curves, okay? Well, okay, so now what you can do, to really solve the problem of where do I start, I use the following information, which is basically that phi should always attain any value from 0 to 2 pi. That's a property of closed curve in 2D. Okay, so what do I do? Basically, I'm basically in 3 dimensions. Okay, and then I have one condition. I'm actually in 4 dimensions. I have one condition from this equation. So a surface in 4D is going to give you a 3-dimensional space. And then I'm also going to use the fact that phi should actually will attain any value from 0 to 2 pi. So I can slice this 3-dimensional space with a plane which is phi equal to constant, and this is going to give me a set of lines which are the initial condition I can use to identify this limit cycle. So now I solve this problem because basically what I did, I can pick basically any phi 0 in S1 because I know that I'm looking for closed curves, and if you look at the tangent vector of this closed curve, phi will attain all the values from 0 to 2 pi. Okay, so now I can pick this phi 0, and I can seek closed solution of this thing just by doing whatever I told you. So you start from 4D. This is going to give you a condition that always is satisfied. Basically, this is basically a surface in 4D, it's a 3-dimensional surface. And now basically you cut it with a particular phi equal to 0, a plane, and now you're going to get a set of lines. For every parameter mu, okay, I'm going to have the set of lines such that if there is a limit cycle here, it's going to pass through these lines. Okay, so now I sort of resolved this issue, because basically you can say, okay, now if there is a limit cycle that doesn't stretch, let's say mu equal to 0, I don't know what it is, maybe it's the blue one, I think mu equal to 0 is the mu one, or maybe center, the green one. So you pick these 2 curves. By the way, this is a Gaussian data set, so you can compute all this for real data set. So you pick the particular set of points, initial condition, you advect this curve, and you say, do I get a curve that when I start from a particular point, so this is the black curve, I start from a particular point of this, there is going to be one of these points such that when I do this integration, I'm going to go back to the same point, which is here. If I do that, I'm done. I computed the limit cycle, and I know that there is no arbitrariness on this, right? So basically now I sort of resolved this problem just using the topology of the fact that basically this is a closed curve. I mean, the details are not very important. I just want to give you a little bit of the flavor of what you want to do when you want to define some of these coherent structures and some problems that you have to overcome. And by the way, in this paper, there is a code available to compute all these structures, okay, in GitHub, or in our group website, there is in the publication list. Usually there is code available here. You click and it drives you to the GitHub code. Okay, again, this is I don't want. This would deserve a dedicated lecture just to explain, this problem. It's not the important thing. The important thing is that give me rate of strain. Okay, and I will tell you a code that can resolve this issue and can compute all the possible limit cycles that are available. Okay, so I told you the story for elliptic Eulerian coherent structures. Of course, in this code we computed all of them. So the Lagrangian coherent structures of finite time influence, the parabolic and the hyperbolic for all of them. So basically, each of them will have a different metric. So you just have to plug in a different metric here. And we also have additional, sections in this paper. When your velocity is given by a stream function, then we prepare this formalism just using the stream function. So there is a little bit, you can look at the details and, or use the code. Are there questions? I just want you to just follow the philosophy of it. Okay? Okay, so basically these last two slides were just a technicality to overcome this problem, which is what I discussed with Anupam. Even in a simple two-dimensional velocity field, it's not easy. If you have a very big domain, it's very hard to understand where are the limit cycles. Okay, it's a very laborious thing, because usually what people do, they start setting Poincare sections in this domain, and then you start advecting trajectory of whatever dynamical system. This is the dynamical system that comes from Euler-Lagrange and your variational problem, and then eventually you want to look for points where things will go back and close up. Okay, but the problem is that how do you pick these Poincare sections? Limit cycle could be very particularly shaped, and so it's really a big problem. This is a way to solve it, at least in 2D.
And also, one cannot predict the shape.
You don't know the shape. You don't know where they are. You don't know if they're small or large. I mean, it's a very challenging task. Okay. This is a way we solved it, at least for 2D and for these direction fields. Okay, so what I want to do now, I want to go back to the polar vortex. So what we did now, we have this code, and we just looked at data set in the atmosphere. Again, as I said the other day, atmospheric data sets are mostly stratified, and usually fluid particles, I mean, of course, they're not completely stratified, so you're going to have flux through these surfaces, but most of it is basically most of the motion is restricted on isentropic surfaces. So these isentropic surfaces are surfaces of constant potential temperature. Is a particular quantity that is relevant in atmospheric science. I'm definitely not an expert in that, but the potential temperature is basically an equivalent temperature telling you that, if you should bring a particle of a particular density and with a particular pressure level to a particular reference state, what temperature would you bring it to? It's not really important for us. For us, the problem is that there is flow that is mainly stratified on two-dimensional surfaces, and when you go into this available atmospheric data set, you get velocities on some of these surfaces. Could be constant pressure, constant temperature, isentropic, potential temperature, etc. This is what we did.
This data is available.
It's available, it's public data, so that's what it is. It's in the paper. I bet now, 10 years later, there is way more refined data, but yeah, there are very good, models for this data. And these models, what they do, basically, they solve massive atmospheric science equations, and they assimilate observations. So it's a basic surrogate things, very complicated business. So.
The scales are huge.
Yeah, the scales are huge. Yeah. Okay, so what we tried to do basically is trying to address this problem. I think this is basically so I think in December 2013 I started my PhD. Basically, I think so. Yeah, yeah. Yes. And basically, there was this exceptional cold that was all over the news, and we're saying. Okay, but was this cold generated by airs funneled by higher altitude to lower altitude? That then, this is like a cone or a funnel that brings cold air from high up to the surface of the Earth, and then if this vortex that is basically typically centered deforms towards northeast of the US, there could be a very strong signature that the cold air was coming from the polar vortex. Okay, so that was basically one hypothesis, and the other hypothesis is that is the so-called North Atlantic Oscillation. Basically, those are very cold air that come or travel on the height of like very close to the ocean surface. So this could also be a cause of this exceptional cold. Okay, so I said, okay, let's try to see if we can compute these elliptic Lagrangian coherent structures. If you can see that it deforms towards the northeast of the US, if that's the case, because these are material structure, that means basically that move with the flow, then if something cold is inside, it's going to be carried with them. Okay, and then the other thing is that this cold air gets funneled through to the ocean surface, and it's more complicated than that. I don't know much of atmospheric science, but basically this was our guess. And this is what we found. Using this basically atmospheric data, you see basically that a week or 10 days earlier, the polar vortex is pretty much centered as expected. But then when there was this exceptional cold, it was very much squeezed towards the northeast of the US. Okay, and this was a result that was pretty much unexpected, because basically people were thinking, or the general idea is that atmospheric flows are very chaotic and turbulent, and therefore it would be very unlikely that you can really find a curve or some vortex boundaries that will stay so coherent for I don't know 10 days or 2 weeks. Okay, and why was this? So why we were really, these structures were not found before, just because people were trying to use techniques that were designed to address other quantities or were a little bit more ad hoc, while instead this method framed the problem and asked what are the curves that will not stretch. Okay, so we really asked for these curves. You solve the problem, and then if they are there, that means that basically this has a much higher likelihood of finding them, these methods. Okay. Okay, so this is basically the evolution of this vortex. Of course, is off scale. This is the Earth, and just for visualization. And then another way to understand if we are really getting the edge of order versus chaos or disorder, what we did, I just stepped a little bit of a little outside belts to this coherent vortex boundary, which I'm coloring in different colors here, and then I let it go with the flow, and despite this perturbation is very tiny, right, this perturbation is really a percentage of the size of this vortex, still they actually exponentially stretch. So this is really telling you that from a regular or from a general time-dependent velocity field, you can extract the outermost boundaries of exceptionally coherent regions. Okay, so this is a way that you can use to identify coherent regions in your phase space. Also, if this is not fluid anymore, it doesn't matter. This could be evolution of phase space. It could be other variables, but the techniques just applies. Okay, so then what we did, we basically looked at other, this quantity, guys, just looked at velocities. They had no other information. There no temperature information, ozone, depletion, whatever, all the properties that are important for atmospheric science. And in fact, if you then go back and overimpose basically these boundaries with what people think are important, sometimes you can get very good matching. For instance, you see that this boundary is actually encapsulating a very big blob of cold air. okay, compared to the surrounding areas. And this is basically just at one particular height. You can do this projection at, you know, very different heights. The data is available online. This may also be important for ozone depletion or ozone concentration, the material transport of things. I don't know the details of the physics or the atmospheric, you know, science part of it. It's also, you can also show that actually these regions will encapsulate regions of potential vorticity. Potential vorticity, my understanding is that is very important for these flows because it accounts for vorticity, but also for the fact that the Earth is rotating and there is stratification. So that's basically what the relevant quantity to look at. I mean, the details are in the paper. Again, I'm not going to go into the details of these quantities, but the only thing I want to take home is that despite you just use velocities, these quantities predict, or actually they will tell you where also interesting other observables may be, okay? And just as an example, you know, in many books of turbulence, even the very, you know, established one, sometimes you see plots in which people say, oh, you know, there are vortices, how do I identify vortical structures? And they look a lot of at quantities like a cube of ice or the Q criterion. This is basically a cube of ice is a quantity that tells you vorticity square minus the strain rate square, the largest eigenvalue of the strain rate square. The philosophy is that whenever this is greater than 0, that means that vorticity dominates strain, and therefore I'm in a vortex. Whenever it's less, I'm in a strain-dominated region. And in 3D, this quantity is called basically the Q criterion. It's a similar philosophy. And then, you know, in these books you can, or, you know, even in several other applications, for instance, in oceanography, people look at, I don't know, for instance, when you have, I don't know, let's say you have a vorticity field, let's say you compute the cube of ice field, right? And then you want that this is very, very positive for identifying where the vortices are. Then you pick a threshold. You say, okay, I want 99% of the distribution of this cube of ice field. So let's say vorticity, where are the regions that the cube of ice is much positive are the vorticity, you know, the vorticity dominated regions. And then you want to say, okay, now I have a scalar field, how do I identify boundaries? You cut the scalar field by a particular threshold, okay? That's basically, so if you do the cube of ice basically is omega squared minus rate of strain squared. Okay, this is a scalar field, so if you plot it on longitude, latitude, you're gonna get something like these things, right? I mean, okay? And then you say, okay, whenever it's much greater than 0, there is gonna be some threshold that you pick. Then these are basically the vortical regions. Okay, so you say, okay, you know, now this is basically the boundary of a vortical region, and they can also have irregular shapes, etc. Then you play a little bit with this threshold, and then you say, this is how I identify vortices. But, okay, so then you can play a little bit with this, but this is basically how many people do it, and this is what I did here. So what I did here for any layer, okay, on this constant isentropic temperature, I picked one of, I picked basically you know, a threshold using whatever method was established in the literature. Usually you pick this threshold based on some statistics of the distribution of this height. Okay, whatever, you know, is used, and then I plot this vortex boundary, and I do it at different heights because this is basically stratified flow, and this is what you get. Is basically you would get a vortex boundary from potential vorticity. That was basically my understanding is what people were using as a metric to identify vortex boundary, and you can see basically that this is very much jumpy, okay, while this is very coherent. Because this is basically now an Eulerian assessment based on thresholds. Okay, instead this was designed to tell me where are the regions that are moving and deforming coherently. Okay, so watch out when when you look at vortex boundaries, especially Lagrangian vortex boundaries for finite time intervals, and you look at just heuristics like Kubowice greater than 0, etc., have to be careful. This Kubowice is nothing. There is nothing wrong with the Kubowice. It's gonna just tell you, in this particular region, vorticity dominates strain. That's all you can claim about it. If you want to abuse it and say, okay, this is a vortex boundary and I can use it to understand how the vortex evolves, that you have to be careful, okay? Just because it was not designed to tell you that. Okay, questions? Okay, so yeah.
So suppose for the skew criteria or Kubowice criteria, if you say that I will reduce my threshold value,
yeah.
Do you think it will improve or no?
No, we extensively explored all of that. Yeah. The other thing is that the Kubowice is not even objective. So if I'm in a rotating frame, I can spin the vorticity as much as I want, so I can eliminate the zero level sets. Yeah. So that there are several caveats. It's good if you really want to say, okay, if you want to address where does vorticity dominate strain, then you look at the Kubowice. But if you really want to understand long-lived Lagrangian vortices, etc., you shouldn't use a Kubowice. And there are also much trivial examples in which positive region of a Kubowice can be in extremely high strain dominated region, extremely high strain region. So basically, in the when I mean strain, I mean not strain rate, but I mean the Lagrangian strain. So basically, you can have that the Kubowice greater than 0 sits in the chaotic region of the FTLE. That means basically that right there, material will stretch exponentially, but the Kubowice cannot capture that. Okay, for many reasons. One is because this is instantaneous and these are instead Lagrangian, and second, perhaps also because this is frame dependent, while stretching is frame independent. So there is a problem there if you want to use this quantity. Yeah. Other questions? Okay, so what I want to do now is, this is basically another type of coherent structure, the elliptic Lagrangian coherent structure, but I want to give you also another example of different types of coherent structures that were not contained in the schematic that I showed you before. And these coherent structure actually are based on curvature, on bending of fluids, not stretching. Okay, and the motivation for this was the following. So basically, if you want to study aerodynamic separation, what happens is that, you have basically a flow. This could be a wing profile, but this is very important also in biology for the flight of birds, or if you want to design, morphing or deformable robots that fly. So the idea is that there is going to be an incoming flow, and then whenever this flow detaches from the wing, then you're going to have lack of performance, you can have stall, you can have also catastrophic effects. It could also cause, immediate loss of lift, and therefore, this object flying is gonna precipitate. So then the question is, we wanted to identify, how do I identify the onset of flow separation? So if I'm basically, let's say you are in a wing profile and you have sensors and you want to identify when this flow separation is at its onset, and you want to identify the onset because then perhaps with flow control you can eliminate this emergence of the separation, because if you don't eliminate it quickly, you lost performance and you can have much more problematic effects. Okay, so this was a problem that really fascinated me and really made me rethink how much you can really use from asymptotic structures, like what we said the other day, when you want to study things that happen over short time or finite time, like Lagrangian time. So this is the problem. So you have a cylinder, you rotate it at some particular constant velocity, it's going to go to steady state, and here I have a viscous fluid. And this viscous fluid there's gonna be a generation of velocity because there is gonna be some drag between this cylinder and the fluid. Okay, you can solve analytically this equation. This was done. It's called creeping flow, and this is the streamlines that you get. Okay, right? This is the cylinder, everything rotates in one particular direction. Those are the streamlines. And the streamlines are the trajectories for steady flow. This is as simple as it gets. You have a two-dimensional dynamical system, which is like this, x dot equals v of x. And this is it. So it's really time independent. So these streamlines are the trajectories. And then okay, so let me give you a little bit more details. So here there is no slip at the wall. So there is no slip boundary condition. So these are all fixed points of the velocity field. But then there is going to be another particular fixed point, which is called Prandtl point, which is very typical and very important point to study aerodynamic separation in the asymptotic limit. That is basically where the unstable manifold to this fixed point departs. This is the unstable manifolds, and then you reconnect here. Is it clear? So this is really what we looked at the other day. So those are all fixed points. This is going to be a particular fixed point that is going to have an unstable manifold that departs. Remember, the unstable manifold is the curve such that you leave the fixed points after infinite time, or in other words, after infinite time, you arrive at the fixed points through the unstable manifold, which is exactly what we discussed the other day on the, in the example. Now I ask you this very trivial question. I ask you, if I start with layers of fluids here, let's say layers of initial condition, I layer them here on this box, and I ask, where is this kink or spike gonna form? Okay, I told you everything. I told you that this is a set of fixed points. This is the Prandtl point. This is the unstable manifold of the fixed point. And now I say, I want to layer set of initial conditions here, and I ask, where is this spike going to form? Is it clear, the problem? Okay, so where is it? I want you to guess. Guys, is it clear, the question? So these are the trajectories, I already know, but now you say, okay, I have a velocity field, I release these initial tracers, these are basically a bunch of tracers, and I want to ask, where is it gonna start peaking?
Maximum value of straight rate tensor.
It's an interesting point. I think I got stuck doing that for a couple of months, and it didn't work. Okay, it's a very good point, right? Any other guess? I mean, anyone wants to guess and say, oh, but this is the unstable manifold is going to start kinking here. That could be a very legit thing. This is what also I was expecting. Any other guess? Okay, so this really, I mean, let me show you basically what happens. This is such a trivial system, okay? If you let this go, something is happening here, and eventually things will go here because this is going to be the asymptotic structure. So eventually this is going to be the unstable manifold. This will be the attractor, okay? But something was born somewhere else, okay? So now the problem is that most of the theory of aerodynamic separation were developed for asymptotic structure in the past. But think about it, where you are in a current real life scenario, first of all, the flow will never be like this. So if you are after structures that exist only for asymptotics, it's a lost game, because with any disturbance, etc., I can start to design all my controller to tweak or eliminate this point, but eventually I will never have this point because the flow is always adjusting, etc., right? First of all. Second, you have to wait infinitely long, strictly speaking, to reach this point. Instead, flow control should be very quick. So what we were trying to understand, I said, okay, but I really want to understand where is this onset, what's happening at the onset, okay? So now your point is an excellent point. I was playing because I already developed the Eulerian coherent structure, so I said, okay, I'm done. I'm gonna use it here, and I'm done. And this project basically started from, a sentence from George and say, do you think we can actually identify the birth of separation? And I actually managed to finish it at the end of my PhD. I tried so many things to identify this problem, and they never worked. They worked for one example. I tried another example, and it was not working. Okay, and eventually, I think eventually I said, okay, but what do I really have to look for? Okay, and if you really think about it, what's the distinguished feature from this configuration to this configuration is really the development of curvature, not stretching. Stretching is a peculiar thing. It didn't really work, stretching in this case, also because basically here, the flow is very slow close to the wall. Okay, so then I said, okay, I really need something that tells me where are the regions that will bend the most. Okay, and that's basically what we did. So the birth is here, the asymptotic part is here. This was a big lesson for me to say, hey, whatever asymptotic structure will tell you, they play the role only if you are stick with this asymptotic, time-independent system, and if you wait for infinite time. If you are not in these two conditions, forget them. Because I wasted basically 4 years. Not 4 years, but I tried so many times and nothing was working. And eventually I said, okay, let me sit down and rethink what's the problem, what's the coherent notion here. Okay, so that's okay. Let me look at distinguished increase of curvature, because for every of these layers, these points are actually likely the point that will bend the most. Okay, and that's basically what we did. So okay, now what I have to do, I have a velocity field. This is basically x and y. So this is basically the fluid domain. That's time. We already used this, extended phase space several times. And now I said, okay, I'm going to have a curve. I call it R. Sorry, R prime is the tangent. And now the important thing is that I was not able to just use the flow map and the Cauchy green, but I had to go to higher order derivatives because folding is not included in first order derivatives. Okay. So then I asked, okay, I want a formula that tells me start from any curve gamma. We are going to find the curve later, but start from any curve gamma. This is going to have a particular distribution of position, R of S, anywhere, tangent, and initial curvature, which is, kappa 0 of S. Give me this curve, let it go with the flow generated by the velocity field, and now I want to understand what's the curvature at this final point. I have a map that maps all these initial position, tangent, and curvature to the final one, okay? Because you do the calculation and you can basically compute the evolution of curvature. Now, again, the details are really not important. The only thing I want you to appreciate is that when we did the Taylor expansion of the flow map, we stopped at the first order. So we stopped at df. Now this is gonna have second order gradients of the flow map, okay? Okay, so that's basically what you have. It's okay. This is basically the Lagrangian, evolution of folding. To give you an example, this is basically what you have when we did the largest stretching. That was basically, I don't know, zeta 0, Cauchy green, zeta 0. This is the equivalent to understand bending. Okay, and you can also look at the Eulerian version of this. Usually looking at the Eulerian version is important when you want to react immediately, but also to get a better intuition, because this F now has integrated many things, so it's very hard to disentangle what's inside. When you instead look at the Eulerian curvature rate, you see basically that there are interesting features here. This is going to tell you that relevant to bending rate, there is a gradient of the rate of strain. So the gradient of the rate of strain is going to tell you with some projection on R prime, the normal, etc. Gradient of the rate of strain is important to understand bending rate. Gradients of vorticity. This was beautiful because vorticity is frame dependent, but the gradient of vorticity is not. So if you start going to a reference frame that spins, I can tweak the value of omega as much as I want. But the gradient of it, no. So the topology basically of the omega scalar field, not. You can play with the height, but not with the thing. And whenever basically I was playing with I was deriving this and I saw vorticity, I panicked because it's vorticity is frame dependent. Square root 1, this is not a good metric. Instead, you can show actually that the gradient of vorticity is frame independent, okay? And then you have other properties like, this is the divergence of the velocity, the stretching, and this is basically a very interesting formula that is objective, frame invariant, and combines stretching and rotation, okay? So now you use these results, and then, I skip all the, the way you compute basically the backbone of separation, but this is what you get. You can actually compute this, what we call basically backbone of separation. So this is going to trace and tell you basically where is this separation getting birth, and then eventually it's going to get basically attracted to the asymptotic structure. And you can also understand if this point connects to the wall, which is very important because we call this basically spiking point, and we have closed formulas to understand, to compute this point for real-time application. So in real-time scenarios, usually in a wing profile, there are pressure sensors on the wing, and then we sort of provided exact formulas to understand where this point is. Why is this important? Because if you know where this point is, then you can actuate or do flow control in a way that you disturb it or you break it in a way that you don't have this point. Okay, so there is basically no flow separation. And this now works for many systems. So this is basically the trivial system. It also works on a von Karman for vortex street. Again, you can see that this is where the separation gets, the birth of separation is not really the classical point, which is Prandtl point. And yeah, there are basically other results here. And the other thing is also that if you don't care about flow separation, these are, I think, very neat formulas to understand folding in fluids, which is a very interesting thing. It doesn't care about separation at this level. Okay. Okay. So we use this in different setup. So we use this for very highly unsteady separated flows where you have a jet that basically gets pushed onto a plate, and then you have these old separation structures. You can have basically free discs that are rotating and they are suspended in a fluid. You can also do this with ellipsoids, where basically on this flow. We also applied it to NACA profiles with the group of Gustav Jacobs, which is a big expert in high performance numerics for these things, and you can also identify where these backbones are, and they connect. So now if you're interested in understanding how a surface folds in 3D, not a curve in 2D, then we extended this theory and we developed some formulas to understand, how the principal tensors that will tell you, for instance, the curvature of a surface. So if you have a surface of initial condition and you let it go with the flow, there is going to be basically different foldings of this surface. There's going to be principal curvature directions and principal curvatures. So we developed a theorem similar to what we did for curves, but now for surfaces, and then you get very interesting, mathematical expression that you can use for understanding folding. Also, if you don't care about separation, and then we also looked for understanding separation in 3D. In this case, you can have either ridges of separation or spikes of separation. So this could be either one-dimensional or two-dimensional structure, and we apply it to several flows, and this is what you can get. Basically, in a flow past a cylinder, you can get where these structures are. Okay, but I think for this, for us, if you're not interested in separation, I would say that these formulas are still interesting to have closed formulas. I will spend the last few minutes to tell you a last story about coherent structures, which is something related to active nematics. And so what we did basically is, so now this is over. So it's just a different type of coherent structure based on folding. It's another philosophy of, first of all, you have to sit down if you want to develop some of these, methods, and say, what is the right metric or quantities that I have to look for my particular problem. Don't try to use something that is already there, if it's not really exactly fitting your problem, because otherwise you're going to spend a lot of time without getting, interesting results. And now I want to instead go back to the finite time Lyapunov exponent, or the hyperbolic coherent structures, and use it not on fluid flows, but on active nematics. And in this case, basically, you can have, interesting observations associated with topological defects. So in this, basically, last few minutes, I'm going to just look at the velocity field in X and Y from liquid crystal active nematics. And I'm going to look at the presence or emergence of attractors and repellers. Now, after these few lectures, we know that attractors are based at the current configuration or at the current time. Repellers are based at the initial time. We already know. And also, inspired by this formula that we developed for bending of fluids in 2D and 3D, I was also interested in understanding how does a little patch of material folds. Okay, not only the stretching that is encoded in the reference frame in the first order derivatives. If you want to understand, basically this is an active nematic from Zvonimir lab, Zvonimir Dogic, and then you can sort of try to understand how these patches or photo bleached basically patches will stretch and fold. Okay, and their dynamics over time, where they are the regions basically that fold the most, they stretch the most, etc. And the interesting thing that we found is this one, is basically we found that, okay, we already know that ridges of the backward FTLE are the attractors, and they will basically actually attract over time patches of fluid. So this guy was a patch of tracers, which is colored magenta. I initialized, at the initial time as basically a circular patch, and then the more you basically go over time, the more you see that this patch will try to converge to the attractor. Okay, this is not surprising, we already knew. But then, in this case, we were also able to connect the dynamics of LCS or attractors to topological defects, which are these guys. So the plus 1/2 is in red, the minus 1/2 is basically in a triangle in magenta. And what we started to have as an observation was that, okay, I see that basically this defect is gonna move and is gonna steer the attracting LCS. They are, like steering objects of the attractors, and the attractors themselves will shape material motion. Okay, and this was basically an interesting observation, which was actually also consistent with a work that appeared a year before from the group of Kevin Mitchell and Linda Hirst at UC Merced. Okay, so now you can have a way to connect topological defects with attractors, and we also looked at this in active 2D turbulence from the equations from Luca Giomi that already Anupam presented to us, and this is what you get. Basically, you're gonna get these ridges of the FTLE. Okay, and this is the evolution of these ridges, and then you have basically the evolution of defects, and you can really see how the defects are really steering these ridges, and this is, of course, is gonna, because it's turbulent, there is a lot of chaos. So eventually, with this periodic boundary condition, the chaos is gonna fill all the space. Okay, but before,
so
yeah.
So you compute these Lyapunov exponent and you just so it is the same definition, right? So that's why
Same definition, yeah.
Because you're integrating it over. There is a division by time, right? So you have log of lambda max divided by.
Yeah, I don't remember. I don't know this particular time, because usually here the Lyapunov exponent should go up because there is really exponential stretching here. Yeah, so I don't know what is. Maybe here I renormalized something, but I would expect that here the Lyapunov exponent.
What happens in the growth? So maybe at all the times it may not be growing exponentially. So there could be like growth and then some.
In this system, I don't think so, Anupam, because it's really at very high alpha.
Okay.
So here it's really, but yeah, I can look it up. I'm actually it's already in the reference, but I can look it up, yeah.
Because looking at one data set, and I felt like maybe the growth may not be as exponential with time. I don't know. Yeah,
this system it is, because it's really very high activity. You can also see it from the dynamics of the flow. Yeah. But yeah, I mean that doesn't really matter. I look this up. Yeah. So here basically we found that the Eulerian positive defects move and deform the attracting Lagrangian current structures, and therefore this was basically a way to start connecting, topological defects and quantification of orientational order with FTLE, and something that we can also think of as a positional order, or order of material transport. And yeah, so basically we also looked at the folding in the corresponding of defects, because now we know all the equations to quantify also folding, and I think this is something similar to what I just showed. So this is basically you put a blob of material, it's gonna stretch guided by the Lagrangian coherent structure, and then the defects will actually deform and steer these topological defects. Yeah, this is other observation that we did for understanding the dynamics of folding and stretching at the defects.
What is the left-hand side data?
It's the same data, but now we computed basically, let me see if I have the equation. Here we computed, so let me go back. So now I computed the folding, yeah.
Oh, folding.
The folding, yeah. So I can compute the folding, yeah. And basically what we observed, something interesting, at least, was, we didn't know, is that basically the defects are in regions of very high folding. These defects are in region of very high folding, and this basically, but low Lagrangian stretching, and this basically could have implication on, where cells die, where they undergo, apoptosis, etc., because there could be a lot of mechanosensitivity there, and it's just a speculation, but there is, evidence that, strain, likely so far, strain has been quantified mostly via stretching, but this data suggests basically that folding may be even more important than stretching. Okay, now you can also use it for, because you have formulas to quantify these things. I mean, I didn't update the reference. This is basically the same reference that is published now. Yeah, so that's all I wanted to say. So I hope basically that I gave you an overview of what types of coherent structures are there. How can you try to think about coherent structure or derive coherent structures? There are different types depending on type of coherence or effect that you want to have it on the deformation of tracers. Time of coherence, Eulerian, Lagrangian, asymptotic. And remember this example, so don't really use techniques that have been developed for asymptotic velocities to address things that are not happening over infinite time, because you can get very interesting, discrepancies, and you can basically look at these coherent structures for any types of flows. All the flows that Anupam was discussing, the inertial particles, active particles, etc. And this could be very, room for a lot of collaborations or of future works in any of us research. Okay, thanks guys. Thanks for sticking with us for all these days and coming over the weekend. Yeah.
And of course, you already have, Matthias' webpage. How can you contact him? So also, when you leave the course, but if you are going to do analysis or anything,
yeah,
I think you can reach out to Matthias.
Yeah, and actually, in the website, we have codes for all these papers. Usually have a code with it. Okay, so there is. Let's see if I. So if you go basically here in publication, usually, this guy is also going to have a code. Here is the paper, the code that we shared in GitHub. I still have to update some of them. But for instance, if you want to compute, the traps, the code is here. These are short attracting profiles. If you want to compute the elliptic coherent structures, there is a code here. So just go here, and then there should be all the link to the GitHubs. And likely I'm gonna create a repository, code repository as a separate tab. Okay, thank you.
Okay,